Good afternoon, sir.
Good afternoon,
Hello,
Professor.
good afternoon. हेलो गुड आफ्टरनून। आवाज आ रही है?
हाँ हाँ ये आ रही है.
हाँ ठीक है।
Shall we start?
Garima, please introduce, sir.
Yes, sir. Yes. A very good evening to all. Welcome to day 613 technical session of 6 days online faculty development program on electric vehicle and charging station technology for sustainable development, sponsored by AICTE ATAL. And our resource person for this session is Professor Akshay Kumar Rathore. On the behalf of the organizing team, I welcome you, sir, in the today's technical session. Before you start your expert lecture, I would like to share a short biography of you to the participants. Professor Akshay Kumar Rathore, IEEE Fellow, received the Master degree in Electrical Machine and Drive specialization from Indian Institute of Technology, BHU, Varanasi, India, and the PhD degree in Power Electronics from the University of Victoria, BC, Canada in 2008. He is currently an expert in power electronics and control of electric motor drives. He had two subsequent postdoctoral research appointments with the University of Wuppertal, Germany, and the University of Illinois at Chicago, IL, USA. From 2010 to 2016, he was an assistant professor at the Department of Electrical and Computer Engineering, National Institute of Singapore. And from 2016 to 2021, he was an associate professor at the Department of Electrical and Computer Engineering, Concordia University, Montreal, QC, Canada, where he was listed in the Provost Circle of Distinction in 2021. During 2020 and 2021, he was a graduate program director and chair of graduate awards. He has authored and co-authored about 300 research papers in international journals and conferences, including around 100 IEEE transactions. His research interests include analysis and design of novel current fed converters, source switching design, and modulation scheme for the DC-DC converter and multi-level inverters. He was the recipient of the gold medal for securing the highest academic standing in his master's degree. He was also the recipient of the 2013 IEEE IAS and Drew W. Smith Outstanding Young Member Achievement Award, 2015 Isayo Takasi Power Electronic Award, 2017 IEEE IES David Irwin Early Career Award, 2019 IES Publication Service Recognition Award, 2020 IEEE IAS Outstanding Area Chair Award, 2020 IEEE Bimal Bose Award for Industrial Electronics Applications in Energy System, and 2021 Nagamori Award. He was recognized as Distinguished Alumna Award in Young Achiever category from IIT BHU Varanasi in 2023. With this, I would request our expert, Professor Akshay Kumar Rathore, sir, to kindly enlighten us with his words of wisdom. Please, sir.
हेलो, आवाज आ रही है ना?
Hmm.
Yeah, let me share my slides. अभी स्लाइड दिख रही है?
हाँ विजिबल है, दिख रही.
स्लाइड दिख रही है ना फुल स्क्रीन?
हाँ हाँ फुल स्क्रीन.
और स्लाइड मूव कर रही है ना?
हाँ मूव कर रही है.
हाँ ठीक है. So good afternoon everyone, and thank you for this second opportunity to speak at NIT Jamshedpur. And last lecture was more into active front end AC to DC power factor correction rectifiers for EV charging application. Okay, so that is basically a power electronics and a control scheme. Now today we discuss basically multifunctional sustainable EV charging. Let me see if this is correct file. Yeah, this one. Okay, yeah. Okay. So I will in my slides I will cover basically that what is the meaning of multifunctional and what is the meaning of sustainable. But since this FDP on EV charging, so the targeted application is electric vehicle charging. Okay, so multifunctional means, suppose for example today if you purchase an electric vehicle, so majority of us they receive an EV with AC port. It means we can connect it with either AC outlet of our grid, or we connect it to the connectors, for example CCS2 connector, etc. Okay, yeah. But there is a possibility in future that suppose if you have solar energy, solar panel in your house, or there is a solar infrastructure as a municipal or commercial parking systems for, and there you can do your EV charging, then solar output is DC and battery is DC. So that time there is a possibility that your car should have a DC port also, so you can connect the DC port in order to charge your EV battery from the solar. Okay, yeah. So the first is the conventional one, grid to vehicle, where you need to have an AC port because grid is AC. Okay, so you connect basically to the AC port, which is grid, and charge your battery, electric vehicle battery. Second option, you connect basically your port to solar, but solar is a DC port, right? Solar output is DC. So you can connect that solar DC to charge your vehicle battery. Okay. Now another option is that, for example, if you are on highways and suppose your EV is out of charge, not just because you have consumed the entire SOC, sometimes it happens because of the temperature condition also. Okay, in cold countries like I came from Canada, and even in India, in Kashmir, Himachal, Srinagar, Garhwal, Uttarakhand area, there is a possibility that in winter, because the batteries have leakage, so battery charge can basically can go out. Okay, it means the battery SOC leaks although you are not using it. Then in those cold countries, then people basically either use a jumper, the booster that they keep in their car all the time, because 6 months they have low temperature. Okay. Or if it is not there, then basically they connect with the electric vehicle of another consumer, and then they charge their vehicle from another vehicle. Okay. So remember, like in our timing, or even if now somebody is out of the petrol in their two-wheeler, in their bike, they just borrow basically some petrol, and then they go to the pumping station. Same thing here. You are just out of charge. You are borrowing the charge from someone so that you can go to the charging station. Okay. So that is vehicle to vehicle charging. So this is multifunctional. So now we understand that G2V is AC to DC converter. S2V is also a DC to DC converter. Oh, sorry, G2V is AC to DC rectifier because grid is AC. S2V is going to be a DC to DC converter because solar is DC, and vehicle to vehicle is also going to be a DC to DC converter because both the sides you have battery of one vehicle, battery of another vehicle. Okay, so what should we do? Should we have two chargers inside the electric vehicle? One is basically doing AC to DC rectification, or another is DC to DC converter, which is doing basically solar based EV charging or vehicle to battery based EV charging. Okay, so what should we do? Should we have two, or we should go for some another solution? Okay, yeah, but this offers you a roaming solution. Okay, suppose for example, if you are driving on highway, if you are not getting a grid based charger, for example, the charger you find on the way is basically solar based DC charger. So if your EV support that, or if your charger support that, you can even stop by and you can charge your EV basically through that solar based EV charging system, rather than going somewhere to wait for the grid based AC charging system to come on your highway. Okay. Okay, so one thing I just mentioned, that grid based grid to vehicle is AC charging, solar to vehicle is DC charging, vehicle to vehicle is also DC charging. So you need basically different power converters. For grid to vehicle, you need AC to DC rectifier. Okay. In the last lecture, I covered that we cannot use diode based rectifier because diode based rectification gives you large amount of harmonics. Okay. Now, and then we had studied that we go for controlled rectifier, where instead of diode we use at least one active switch that can do wave shaping. Okay, that can do wave shaping at the input. So input current is basically shaped at sinusoidal, so that we receive a high power factor and low distortion. So this is the requirement. Okay, so power factor should be unity if it is a grid to vehicle charger, and power quality of the grid current should be quite high, means total harmonic distortion should be less than 5%. As well as another requirement is that none of the harmonics should have distortion value more than 3%. Okay, so total should be 5 and any harmonic component should not exceed 3%. Okay, so these are some IEEE standards. Okay, yeah. So all the chargers or all the products in the market should respect these standards guidelines. Okay, yeah. So when it comes to solar to vehicle application, okay, S2V charger. So we just notice that what we need is basically AC DC to DC converter, because solar is DC. Okay, and battery is DC. And one thing that we can see that since it is a low voltage, because solar system like this, like a roof, okay, or like a small shaded area, or in a very small in a very small open space where you are developing a charging station, cannot produce a large voltage. Okay, so since solar cannot produce a large voltage, okay, cannot produce the large voltage, that's why the charging cannot be fast. All of us understand that the current flows from high potential to low potential. Okay, and the value of the current, which is the charging current in this case, depends upon the voltage difference. Okay, so battery has a voltage, for example 400 volt. So if you charge from 500 volt, there will be a current. If you charge from 600 volt, current will be high. If you charge from 1000 volt, current will be further high. Okay, so in order to do fast charging, you need to develop a fast high current. Fast charging, you have to develop the high charging current, and that comes from the high voltage. Okay, but here we know clearly that we are not developing a high voltage. Okay, because solar voltage is low. Okay, in addition, we know very well that solar power density is low. Solar power density is low means a large solar panel does not give you basically 100 kilowatt. Right, most of the people who are trying to have solar rooftop, solar panels in their houses, hardly it can give you 1 kilowatt. Okay, yeah, hardly it can give you 1 kilowatt. So we cannot get 100 kilowatt that easily from a small space. So that is the reason we cannot do fast charging. So AC to AC base, we can see that it is a fast charging, but here, I mean, the solar based system is a slow charging. And one thing that we need to take care during the power electronics design is MPPT operation. Because suppose, for example, the sun condition is such that it is giving you suppose 5 kilowatt. So you need to develop a current, you need to understand that 5 kilowatt peak power, and you have to create a charging current accordingly. Okay, and that is not that simple. Okay, that is not that simple. I mean, it depends upon the technology that we use, but it can be simple and it can be difficult. But MPPT operation is required here, maximum power point. Otherwise, you are wasting the solar power. Okay, so once you decide based on this P&O or impedance method, okay, then we know that okay, currently the peak point or peak power value is this. Okay, so that peak power divided by the battery voltage will be the charging current. Okay, so basically we need sensors, and the sensor can let us know that what is the maximum power coming from the solar, and then divided by the battery voltage will become the charging current. Okay, yeah. Okay, so that we need to implement. Otherwise, suppose if the solar is giving 5 kilowatt, but you are developing a charging current of only 1 kilowatt, then basically you are wasting 4 kilowatt power. Okay, then you are charging your vehicle also quite slowly than expected. Okay, yeah. Okay, so from this slide, you can see that there is a possibility, like I have worked in the past, that we have developed a charger, which is a hybrid charger. Means hybrid charger means it can it can basically act as a AC to DC converter, as well as it can act as a DC to DC converter. Okay, but we can clearly see that at this point, it is an AC port, and we have another circuit MPPT, and that is a DC port. Okay, so one thing you can notice clear, that the charger that you see here, okay, it should work as a AC to DC converter when connected to the AC port. Okay, and it should basically work as a DC to DC converter when it is connected with the DC port. Okay, when it is connected here. Okay, so first of all of you should know that, is there a possibility, or is there an option that we can design a power converter which can work as a AC to DC converter as well as DC to DC converter, both. So here you can see, so whatever written here, charger, this black box, I mean currently it is white box, but it can work as a AC to DC as well as it can work as a DC to DC. Okay, so that is an important part. So basically, I don't know how many of you know it, but basically the answer is yes. Okay, answer is yes, we can do that. Okay, and we have demonstrated. I will show you some results. Okay, yeah. So now let us see. Okay, so solar based charging, like country like India, where we have sun throughout the year, in future it will become an economical and business option, and it is quite important for us. Okay, it is quite important for us because the charging in India, or the solar, or the power generation in India is basically coming from the coal. Okay, so that charging is not sustainable charging. So today's topic is basically sustainable charging, but the charging that we are doing for our electric vehicle is not a sustainable charging. Okay, and the reason is that the power, almost 76% power that is coming for our EV charging is coming from the coal. It means the charging is basically releasing carbon footprint. Okay, yeah. So this is not sustainable. Our mobility, we are claiming to be a clean mobility. Okay, why we are claiming a clean mobility? Because there is no tailpipe emission. And why there is no tailpipe emission? Because we are using battery energy storage rather than the gasoline storage. Okay, but battery energy storage is not coming for free. Okay, once we need to we use the battery, and then after that you need to recharge the battery. Okay, so where is that charge coming from? If that charge is coming from the renewable energy, then it is a sustainable, green and clean mobility and clean option. But if that charge is coming from a carbon, from a coal, from the carbon footprint, then this is not a clean option actually. Okay, so that is the reason that how we can close the loop, make it sustainable, make it renewable, added to this charging infrastructure, so that we really can claim that yes, it is a clean mobility and it is a green charging infrastructure and it is sustainable. Otherwise, charging from the coal-based power generation is not a clean mobility. Okay, because battery itself is not clean in the manufacturing, but after that, if the recharging is also coming from the coal-based generation, then it's another question mark for us. Okay, that's why introducing solar, introducing wind, introducing other renewable energy options, not the hydrogen. Okay, because hydrogen is not renewable energy source. Many people are basically confused, and whenever as an editor-in-chief, I get many papers and they put hydrogen fuel cell as a renewable energy. Hydrogen is not a renewable energy. Hydrogen is alternative energy source. Alternative means it is not a conventional energy source, it is alternative energy source. Because hydrogen is not coming free like a wind, like a thermal, like the solar, or like biomass, or say like shore power, ocean power. Okay, hydrogen you are generating by the electrolysis of water, and then you are storing it. That has lot of energy process involved. That's why hydrogen or hydrogen fuel cell is alternative energy source. That is not a renewable energy source. That is not free. Okay, yeah. So basically, we need to put renewable energy infrastructure into our charging system, so that the charging taken from the grid we can minimize, and charging from the solar, wind we can maximize, and we can say this is clean and sustainable charging. Okay, yeah. So as I said, in future, you very soon, sooner or later, you will see basically 2-port chargers, one for solar or vehicle to vehicle, another basically for grid based one. Okay. Yeah. So from this slide, you can see that based on the, sorry, let me pointer option pen. Yeah. So you can see that based on the temperature. So you can see solar power generates higher power basically in the cold countries. Okay. So in Hamirpur, you will see in Hamirpur, Himachal, it will generate basically high power. Okay. And when it comes to Jaipur, Rajasthan, you will see it will generate less power because Rajasthan is hot. Okay. And Hamirpur is cold. Okay. So if solar is there in Hamirpur and if NIT Hamirpur and if solar is there in NIT Jaipur, then you can see the power generated at Hamirpur will be higher. It means despite it is a colder place, temperature is less, it can provide you more charging current compared to Jaipur. Okay. Yeah. And now insolation part. Okay. So many people think that, okay, sun is hot today, so power is high. No, if sun is hot, then power is low. Okay. Yeah. And another option you can see from here that this is insolation. If solar intensity is large, solar insolation is quite good, then we see that solar output is more. Okay. So it's all the game of insolation basically. Okay. And after that temperature. Okay. Yeah. Now what is MPPT converter here? MPPT converter is simple, either a buck converter or a boost converter. You need not to find basically any high tech. You need not to find basically any high tech power electronics topology for that. Okay. Yeah. You need not to do high tech power electronics topology for that, because as I said, this is slow charging, it is low power, and solar voltage is also low. It is not high voltage. Okay. Yeah. That's why it is a slow charging. So, but you need to just implement MPPT, maximum power point tracking. Okay. Yeah. Vehicle to vehicle charging, which is, as I said, on the highway. Okay. So this is the converter requirement can be bidirectional, as I mentioned here. Either you are charging from this vehicle to this vehicle or this vehicle to this vehicle. Okay, you can do it by unidirectional also, but you need to do swapping of the plugs basically. Okay, yeah. But anyway, this is DC to DC converter, and one thing is that you can do it basically instead of a continuous charging, just by pulse charging, because you are only transferring a small amount of charge from vehicle to another, so that the guy can go home or can go to the garage, or sorry, the garage or the charging station. So it's like this. Suppose it's a zero current and suddenly a high current, for example, 10 ampere. This is a 10 ampere, for example. Okay, and this current has been flown basically, for example, for 10 second, 30 second, whatever, and then just turn it off. So the battery got some charge, and basically it can go to, say, for example, 10 kilometers to the garage. Okay, and or go to the charging station or go home basically. Okay. Yeah. Okay, so this is finally that we can see that, okay, this is multifunctional EV charger. Okay. So this will be a question for you also, again, that did anyone of you work on it? If not, then this is a research topic. You should really consider to do this. Okay. A multifunctional, sustainable, universal EV charging system where a single power electronics infrastructure can support multi-source or mixed energy source EV charging for your electric vehicle. Okay. So right now, when it is connected to the grid, you can see we have a diode bridge rectifier, okay, which is converting AC into DC. And then here we have a PFC. So last time I discussed with you, so this is a boost converter, for example, and that is acting as a PFC, right? If you remember the last one, like this. Okay. So before that, there is a rectifier, and here basically we are charging our battery. Yeah, here. This is our EV battery basically, which is shown here. So this power converter is this and this. So when we try to turn this switch on and off in a sinusoidal fashion, basically, okay, in a sinusoidal fashion, then basically we can see here we will generate a sine waveform. Okay, yeah. Okay, Like this is exactly the same circuit that we discussed last time, that you put a diode bridge rectifier here and a boost converter, and boost converter is operating, the duty cycle of the boost converter is varied in a sinusoidal fashion, so that you can get a grid current, a sine waveform, okay, which is unity power factor, properly wave shaped and distortion less. Okay, so that is working as a AC to DC converter. Okay, now you just see that this is a boost converter, right? So its input can be DC also, and when input is DC, this will just as a boost converter simply. So now when we disconnect this grid part, suppose the grid part is disconnected, and if you connect this solar panel here, then this acts as a simple DC to DC converter, boost converter. So if solar voltage is, for example, 30 volt, okay, by using a boost converter, you generate basically 64 volt. Okay, just by double duty. If the duty cycle is 0.5, then we know that duty cycle is 0.5. Then what happens? Output voltage is 2 times of the input voltage. Okay, 2 times of the input voltage. Then output voltage is higher and it will charge the battery. But only thing is that you need to develop the MPPT technology. Okay, yeah, and which is very simple. Most of the MPPT using boost converter you can see on YouTube, or you can see in Google or literature. Okay, yeah, boost MPPT. Similarly, vehicle to vehicle, here you do not need any MPPT. Here you just need that, okay, the duty cycle of the converter, the duty cycle of the converter should be adjusted to some value so that charging current is not too high. Suppose this voltage is, for example, 42 volt because battery is discharged. So duty cycle you need to be probably, for example, 0.1 or 0.2, so that 42 volt becomes 64 volt and it will charge your EV. Okay, so now probably it is very clear to you that just using a diode bridge rectifier and just using a boost converter, you can develop a multifunctional EV charger. You do not need any hi-fi thing. Okay, you need not to know basically a very hi-fi thing. Okay, yeah. Okay, so a simple diode bridge, a simple boost converter can be a multifunctional EV charger that I just explained. You need not to go through a complex power converter and complex modulation strategy. Okay, so if you read some of our papers, we had demonstrated it, I think, in 2016, 17, I mean, 6 years back. Okay, yeah. Okay, so that's what you can see here. Sorry, I did not know this slide. So you can see this is grid, this is a diode bridge rectifier, and this is buck boost converter. So even in addition to boost PFC, we have demonstrated using buck boost PFC also. Okay, so in case you want to reduce the voltage, you can reduce the voltage. If you want to increase the voltage, you can increase the voltage, because this is a buck boost converter and you can charge the electric vehicle basically. So right now, if you follow this, then you can see this is G2V. But if you can connect solar panel here, right here, and if you connect solar panel here after the rectifier, then you can see current cannot flow. Suppose if somebody think that, okay, current cannot flow from cathode to anode, right? Current cannot flow cathode to anode. So this current will not go to grid side. If solar panel is connected to this point and this point, only way where current can go is the battery basically. Okay, so in addition to boost converter, if we use a buck boost converter, then also you can see that in addition to PFC, if you connect a solar panel here, it can do basically EV charge. It can do basically DC to DC. It can act as a DC to DC converter. Current, because the diode is reverse bias, cannot flow towards the grid side. It will only charge the electric vehicle. Okay, yeah. Similarly, another possibility is this bridgeless choke converter. So many people try to do through isolation. I mean, if I will see if I have some slides where I have put isolated circuits or not. Okay, oh, sorry. Yeah, so choke converter. So I mean, one easy way always to whenever we try to develop power electronics, one easy way always is to basically develop the non-isolated converter. One thing is that you get rid of the transformer design, as well as you get rid of basically efficiency loss due to the transformer core, magnetics, hysteresis, eddy current, and residual magnetism, and copper loss and winding, and space. Okay, yeah, and additional cost of the magnetics. Okay, yeah. So this is a non-isolated converter, and you can see that number of switches is still one. Okay, still one. Okay, sorry. So this converter, you can see that generally people study this as a DC to DC converter, but you can see here we connected here grid AC. Okay, yeah, and this switch we made basically bidirectional switch, because grid current is like this, grid voltage is like this, positive and negative. Okay, so when the voltage is positive, this switch is on, current flows through this diode, and during negative cycle, this switch is on and then current flows through this diode. Okay, yeah, that's why we need the bidirectional switch in order to support the both half cycles of the grid voltage or the current. Okay, yeah. Okay, so we modified the Chuk converter, and we made it basically the non-isolated, because in order to increase the efficiency, make it high density and low components count. Okay, making it transformerless so that the space and cost and losses of the magnetics can be reduced. Okay, and since there is one switch, so we only need one getting signal, because at a time only one switch is on, right? The second switch diode is conducting. So in positive half cycle, the top switch is on. During negative half cycle, the bottom switch is on. Okay, now important thing here is that we used discontinuous conduction mode of operation. Okay, why discontinuous conduction mode of operation? Because it helps in achieving natural power factor correction. Like in the last lecture we discussed about power factor correction is basically an important technology, right? And all of us who works on AC to DC converter, we understand that how it is not easy like a boost converter, or it is not easy like a DC to DC converter. Okay, it is really different. You need to put efforts. That input current is sinusoidal. Input current is in phase with the grid voltage. Input current basically is purely sinusoidal. It does not have any kind of ringing or any kind of ripples or harmonics. That's why you have to design filters accordingly. That's why you have to design the switching and modulation accordingly. Sometimes we need to use sensors. Sometimes we need to use phase log loop also, so that zero crossing of the voltage and zero crossing of the current can be synchronized because of the unity power factor mode of operation. Okay, yeah. So now I will mention that why we use DCM operation, so that you will see the merits of this. Okay. Okay, so basically if you see, robust and reliability will be higher, and now I will show that why it is higher. Okay, so DCM operation is basically, if we, so the continuous conduction mode requires three sensors. Okay, three sensors. Okay, so three sensor is not good, right? Like जैसे हिंदी में बोलते हैं ना कि ये मन भावन नहीं है, right? हाँ, तो three sensors not good basically. If you are putting three sensors, one voltage sensor at the input, one current sensor at the input, because one input voltage is sensing the grid voltage, one input current is sensing the grid current, and we try to see that they both are synchronized or not, unity power factor. And one sensor is the output voltage in order to decide the charging current. Okay, yeah. So basically three sensors do not look good to eyes basically in the hardware. मन भावन नहीं होते actually. ठीक है? Yeah. Now DCM require only sensors. Okay, yeah. And I love one sensor basically. I don't love three sensors. Right? So we love one sensor, जो मन भावन है. Right? Yeah, I love that. So DCM requires single sensor. Okay. So the cost goes down. Reliability gets also improved. Okay. Yeah. Because what happens that DCM at that output basically looks like, okay, output basically looks like a register when it has a DCM conduction. Okay, yeah, and we all love basically resistor. Nobody loves inductor and capacitor, right? Yeah, right. We all love resistor. We don't love inductor and capacitor, because resistor is basically active power. वो है मन भावन, right? And inductor and capacitor is reactive power. Okay, तो वो मन भावन नहीं है. इसलिए we love basically resistor जो मन भावन है, right? Yeah, I love that. So resistor is better because power factor issues are not there, and reactive power issues are not there, and synchronization issues are not there. Okay. So I hope you are understanding that this continuous conduction mode is reflecting any battery load, any DC load like a resistor. And you know, if we connect a resistor, suppose this is a grid, right? This is AC waveform. This is a grid, right? And if you connect a resistor across the grid, so you can see what is the current in that resistor. That current basically is in phase with the voltage, right? That is in phase with this voltage. Now you need not to put any effort. In case of resistance, you need not to put any effort to make a proper wave shaping. Okay, you need not to put any effort basically to synchronize the voltage and current, to synchronize the zero crossing. You need not to put any phase lock loop in case of resistor. It is automatically synchronized and it is automatically basically in the same phase of the voltage. Okay, yeah. No PLL requirement. And since there is no PLL requirement, there is no PFC requirement, it is a natural PFC, there is no zero crossing requirement, then you do not need input voltage, input current sensor, not at all. Okay, automatically the grid current, if we write in words, then automatically grid current is basically following the grid voltage waveform. Okay, this is called natural PFC.
One question I have here. Can I ask?
Yes.
Actually, for DCM mode, we need to take the some value of the inductor, low value of the inductor, right? So when we decrease the value of inductor, so voltage boost cannot be obtained.
No, voltage boost can be obtained. The boost voltage is always can be obtained with CCM, DCM, or even BCM, boundary conduction mode, current conduction mode, and discontinuous conduction mode. In all three, you can do boost mode. There is not a problem at all. As long as input is connected with the source, boost mode will be obtained.
Okay.
Only thing is that you have to decide the duty cycle accordingly.
So only duty cycle we have to say. Okay.
Okay, any questions?
No from my side.
Okay. Sorry, somehow it came out.
Sir, one thing, I have a question, sir.
Can you see a screen, Steve?
Sir, in discontinuous conduction mode, actually we considered that the current, the flowing through the load, or the current which is flowing, that is very low amount. It is flow below the rated. So, and the current is also the discontinuous in form. So because due to this, there is no effect of charging current. There is no effect in condition of the discontinuous conduction mode of the battery charging current.
No, not at all. See, suppose if you want to decide, just to answer this question, that if you want to design a 1 kilowatt power converter, for example, okay, you will starting point is your rating. So for that rating, you can decide either DCM or CCM. It doesn't matter. So if you decide CCM, it will still do 1 kilowatt. If you decide DCM, it will still give you 1 kilowatt. So it will not affect your charging current. All your components will be designed accordingly.
Okay, sir. Okay, sir.
Yeah. So from starting you design. So if you want to design CCM for okay, yeah. So now for this purpose, let us see this G2V operation that we have connected this grid. Okay. So here basically, let me see. Yeah. So these are different mode of operation that when the switch is connected. Okay. When the switch is connected, I mean, yeah, here. Sorry, here. So when the switch is on, then you can see the power flow. Here VGS is on. So when the switch is on, you can see that the current is increasing and the power flow is happening basically through the switch as well as through this capacitor which was pre-charged. Okay, yeah, the detailed thing you will see in our paper because explaining will take really longer time. And when the switch is off, there are two modes of operation where you can see, like in one case the diode is conducting, in one case diode is off. Okay, so in one case basically what is happening, that the current that was stored in this inductor is passing through the diode, and in another case basically the current that was stored in the capacitor is now also passing to the load basically. So here resistance you consider as a battery charger, but here we put resistance because it is a DCM mode, so it is just emulating it. Okay, yeah. Okay, so whenever so now basically we have moved from a two loop system to one loop system, from a 3 sensor to single loop. Okay, yeah. So always important thing is to do the small signal analysis. Okay, I hope you guys know small signal analysis. Otherwise, in future, I will give a lecture on it. It is a very simple process. Okay, many of my students, they published IEEE transactions by doing small signal analysis of a complex converter and developing a very nice control system. Okay, once you are able to do small signal analysis very thoroughly, very simply. Okay, design of a two loop or single loop, whatever you do, we do mostly two loop. Is very simple. It really works and really give very good results. Okay, yeah. So here, since it is a single loop system and single sensor system, so single sensor, single loop, that's why only one PI controller is required. Okay? Yeah, that's what you can see. And what is this? This is output voltage. Now we are not at all looking at the grid voltage. We are not at all looking at the grid current even. Okay, and the getting signal is generated in order to basically control the switch. And what we are controlling by controlling the switch, we are controlling the output voltage, and that output voltage is basically responsible for the charging current, because the charging current is converter output voltage minus battery voltage divided by the internal resistance of the battery, right? Yeah, so once we develop this, okay, by putting in the values of inductor, capacitor, etc., we can get this value, numerical value. And by putting this numerical value and then following the simple process, we calculate the open loop gain, closed loop gain. Okay, then based on the conditions of phase margin and gain margin, then we calculate the value of PI. So there is a standard process basically, which is quite simple. Okay. Hopefully in future I give lecture on that. Okay. Now you can see that we develop a very complex system. Okay. So I mean, here you can see one is input inductor, another is output inductor. Okay, which is here input inductor and output inductor. Okay, here we have MOSFET. Okay, and here is the gate driver chip for that. Okay, here with the DSP we are controlling that. Okay, and here is the voltage sensor for the output, no current sensor, and no input voltage sensor. Okay, and these are the diodes. Okay, and these are basically the capacitors, output capacitors here. Okay, these output capacitors. Okay, okay, output capacitors. And here you can see that we have used 650 volt silicon carbide, so that resistance is less. Okay, and what else we can see here? Yeah, mostly this. Okay, so I will show you some results later, but you can see we tested it, this non-isolated power converter, for 1 kilowatt up to 250 watt. Okay, and you can see our power factor is always 1, and you can see our distortion is always less than 4%. Okay, duty cycle we went up to 0.55. Okay, that comes in the design point, you have to decide accordingly. Okay, because I was in Canada, so we did in Canada for 120 volt power supply, because in Canada the grid voltage is varying from 110 to 120. But the student was master's student. Okay, and develop a very nice basically hardware. Yeah. Oh yeah, sorry. One thing that we use switching frequency 50 kilohertz rather than 100 or more because the converter is hard switching. We did not implement short switching. But since it is a discontinuous conduction mode, so we are naturally getting zero current switching. Because discontinuous conduction mode means automatically the switch current goes to zero, then it stays zero, then again it turns on like this. So zero current switching is natural. Okay. So we receive zero current switching. We did not receive the zero voltage switching. As I was telling you that does it affect the charging current? I was saying that no, because this is your design point. That you are designing a converter for 1 kilowatt, battery voltage is suppose 400, so then your charging current is 2.5 ampere. So it will come 2.5. Doesn't matter CCM or DCM. Okay. Yeah. Only thing CCM, DCM will decide is basically this components value. As I was telling when Dr. Madhu was asking that, then I was saying that you have to adjust duty cycle accordingly. And that duty cycle will depends upon basically the value of inductors you have decided. Okay, for your DCM modes. Okay. Now, as I was saying, this work was done by a master's student, and you will, and believe me, the student was from KIT University, and she was a female, did a very good job in hardware. You can see very nice waveforms, unity power factor mode of operation. Okay. Yeah. You can see discontinuous conduction mode, the current, as I was telling you, like this. Switch on, off, and then zero current. And this is zero current switching, natural zero current switching. You see, zero natural current switching. And you can see this is increasing slowly. So you can see the envelope. This is increasing slowly during positive cycle, and then this is negative cycle. Okay. And then finally it results like this. And you can see the output voltage is this 200 volt DC. So converting AC to DC with zero current switching with DCM mode of operation, power factor is unity. Okay. And you can see that, I mean, this is for, I think, 5 ampere per division. This is 1 ampere. So this is low power. I think this is 1 kilowatt. Probably I forgot to mention. Probably this is 500 watt or probably less. Okay. But you can see doesn't matter the power level. But important thing is that it is maintaining unity power factor of moderation. Yeah. Okay. You can see the distortion we have seen in the spectrum in the oscilloscope. Okay. And you can see that we try to increase the current suddenly. I mean, the charging current has changed from some value to higher value. Okay. Same thing, higher value to low value. But you can see that continuously unity power factor is maintained. It is not going out of the loop and there is no overshoot or undershoot. Or sinusoidal waveform is not changing to non-sinusoidal. Distortion, you can see less than 4% and unity power factor mode of operation. And from here, you can see this is the charging current. This from here to here. And similarly, the grid current that you are drawing from the grid has changed. Okay. But unity power factor, no distortion. Similarly, you can see charging current has gone down. But you can, so grid current that you are trying has also gone down. But unity power factor mode of operation and basically no distortion. Now we have basically done it very dynamically. So you can see high current, low current, high current, low current, high current. Okay. So our control system with single sensor, single loop with proper PI controller is so robust that in every seconds or few seconds we did these command changes, but it was stable all the time. Okay. Okay. And you can see that efficiency, this is our laboratory prototype. We received around 94%. Probably industry can further improve it. Okay. And like the student has done one benchmarking also. I mean, she tried to do with various kind of topologies. Simulation, we did not test it all. Okay. So our was 94 and one converter was a bit higher, which was number 5. Bridgeless boost converter. Okay. Bridgeless boost converter. Yeah. Okay. Yeah. Or probably we should, we can basically find better components to match this difference of 2% or 3%. Yeah. Oh, yeah, here. So like the student has done a benchmarking with many, but majority has used DCM, only one has used CCM, and probably this was the reason that its efficiency was also high. BL boost, right? This is a BL boost number 5. So that was the reason probably its efficiency was high, or probably the voltage or current specifications may be different, because efficiency depends upon the specifications also, because current is something that determines the efficiency, because the losses are I square R. If current is high, then losses are high. So we need to properly select the components accordingly. Okay, now the same converter now we have basically used as a DC to DC converter for say solar based charging or say vehicle to vehicle charging. So now it becomes very simple, because a chip converter for DC to DC is everybody is study, like a boost converter, buck loop converter, septic converter, etc. Okay. Yeah. So we again studied this for DC to DC. So basically switch is on, switch is on. Okay. Now the switch is off, switch is off. Okay. So there are basically 3 modes of 4 modes you can see. So this is 1, this is 2, this is 1, this is 2, this is 3, and this is 4, and 1 cycle is over. Okay. So once you see in the paper, then it will be more self-explanatory basically, because we have given all the details. Okay. Yeah, then it is more self-explanatory that what is happening. Now components. Sorry, yeah. So now basically we did, instead of 120 volt AC, now we have done it for 48 volt DC, and output is still 400. I think previously also it was 400. Let me see. Yeah, previously also it was 400, thinking that it is a 400 volt battery. Okay. Yeah. Okay. And you can see inductor 1.5, still the inductor is 1.5. Okay. Yeah. Okay. So that we are maintaining the DCM. Okay. Same silicon carbide devices we have used. So basically converter remains the same. I mean the components remain the same. Now you can see that input voltage is DC, input current is DC, output voltage is DC, output current is DC. Okay. Now converter is acting as a DC to DC converter. Okay. And you can see that this is charging. Sorry, now this is constant. Sorry, this is just a zoom version of this. So this is, I think, different power rate. This is different power rating. I think it's 200 volt per division, 2 ampere. Charging current is 2 ampere. Here, sorry, these are only voltage, no current actually. And here the charging current is 1 ampere. Okay, yeah. Charging current is 2 ampere. So 2 ampere is, I think, 800 watt, and charging current is 1 ampere, means it is 400 watt. So we tested it for 800 watt DC to DC, for 800 and for 400 actually, rather than 1 kilowatt and 500 watt. Okay. Efficiency, since as we know that AC to DC converter efficiency is lower, DC to DC is higher. So you can see that 94% efficiency is now 95%. We increased it by 1% because DC to DC converter efficiency is higher. Okay. Yeah. So these are just that the student has enough time. So in her thesis, she did very thorough work to determine where the losses were, the individual losses, and then the total losses, so that we could improve. Okay. Now this plug-in technology that we discussed. So actually this I just showed you for one, but we have done it for many other topologies. I think we have done it for at least 3 topologies. I think I showed you a simple one, but anyway, that was plug-in. But we have applied this for a wireless charging also. Okay. Yeah. Okay. So now basically the same technology we have used basically for wireless IPT, inductive coupled power transfer application also. Okay. So basically, I want to mention here that this is the topology we use now for wireless power. So you can see it also looks like a boost converter. You see, this is a input inductor, and basically this is a full bridge technology, current fed. So if you read my paper on current fed DC to DC converter, then you will see an inductor in series is basically current fed converter, then a full bridge, and then basically a diode rectifier. Okay. And then output voltage, DC to DC converter. But now what I'm doing, that DC to DC converter I'm using basically for AC to DC converter. So I just mentioned that earlier, I just mentioned in one of the slide that a boost converter can be used for AC to DC, PFC, and DC to DC boost also, right? So same thing we try to demonstrate then, that a current fed DC to DC full bridge, which is used for DC to DC converter, can also be used basically for AC to DC converter. Okay. Now what I did basically, that this diode bridge rectifier I replaced by a active bridge, dual active bridge basically. Okay. So why I used it active bridge, so that basically I can use it for, let me see if I put it here. I did not. Oh yeah, here I can use basically it in reverse direction also, bi-directional, this direction also, which is vehicle to grid application. Okay. And another thing is very synchronous rectification. Yeah, here synchronous rectification. Okay. So that although the direction is this, vehicle to grid, but instead the current flows from the diode, I want to use the current flow from the switch, because that is called synchronous rectification. The rectification through the channel. Okay. Rectification through the channel rather than the diode, and it is basically preferred in low voltage battery, voltage less than 100. In India, the electric vehicle are basically 48 volt or 72 volt. E-rickshaws are 48 volt. Even our Mahindra E2O is also basically 48 or 72 volt. Okay. So it does not make sense to use a diode rectifier. I will show you why in example. But it makes sense to use basically synchronous rectification. So who is not aware of synchronous rectifier, just study, and you will see that it is used for low voltage output, so that efficiency can be improved. So rather than the body diode conducts, we generally make sure that the MOSFET channel conduct. It is done through MOSFET. It cannot be done through the IGBT, first of all. Okay, always through the MOSFET, because MOSFET is a bidirectional device. In the MOSFET, current can flow from drain to source, as well as current can flow from source to drain. But in case of IGBT, current only flows from collector to emitter. It cannot flow reverse emitter to collector. It is a unidirectional device. Okay. So in MOSFET, basically current can flow from basically source to drain, and that is known as synchronous rectification. Diode is not conducting, and efficiency is higher. I will show you by an example. Okay. Yeah. Now, like as it is, you can use it for stationary charging, as well as we can use for dynamic charging. Dynamic charging is when vehicle is running, then it can be charged basically on the go. So this part, in case of dynamic charging, this part is on the ground. Okay. And this part is on the vehicle. Okay. So since this part is on the ground and it is on the road, then this is controlled by basically the grid. It is always live. You cannot control. Now suddenly, once your vehicle comes in alignment with this, and if you use a diode rectifier, suddenly it tries to charge the battery, and you do not have any control over it. Okay. But if you have a switches here, okay, then basically you can do the modulation of the switches, and then by using the current control, by the current sensor, you can limit the charging current of the battery, so that your vehicle battery do not damage, your components do not damage, because these components that you are using here have a current limit, current rating. If higher than that, then they will be damaged, right? So this is called receiver side control. That also I will show you. Okay. So this circuit can do many things. One thing, either it is high voltage battery charging, then the output bridge diodes are working. If low voltage battery charging, then synchronous rectification is done and MOSFETs are working. And it can act as a V2G also, because it is a bidirectional converter. Okay. It can work as a AC to DC for grid-based charging. It can work as a DC to DC for solar-based charging. It can be used as it is for stationary charging, or we can do this receiver side control, secondary side control for dynamic charging. So a single topology can, at least you can see here, can do 7 or 8 tasks basically. And this is the research problem, that how you want to basically make your thesis. So you have 8 problems and one circuit topology solving the 8 problems. Okay. Yeah. And that makes the good thesis. So my student, Dr. Suvendu Samanta, who worked on this, is right now assistant professor in IIT Kanpur. Very soon he will be associate. And he was awarded the Governor General Gold Medal for this thesis in Canada, which is the highest honor for a PhD degree. Highest honor. Okay. Very difficult to get. Only one candidate in the entire university gets it. Engineering, science, arts, law, management, everything. Only one guy get it, and he was one of. Okay. Yeah. So this is the circuit topology. So as I was saying that here, so this is circuit topology, bidirectional cursor. Yeah. And here I have used resonant tank, which any researcher uses in wireless power transfer in order to improve the efficiency? Okay, yeah. So resonance is required basically in order to tune the two coils. One is transmitter, one is receiver. So this resonance basically tune them so that the pickup at the receiver side can be maximized because they are at the same frequency. Okay, yeah, resonance. Resonance makes basically proper tuning of the two systems because they are far apart. They are not basically electrically coupled. They are magnetically coupled, electrically isolated. Okay, so one is on the ground, one is on the vehicle. So how to do a proper coupling for them? So that coupling is done through the resonance. The resonance on the both sides have basically the same frequency of resonance. If same frequency of resonance, then they can understand each other basically, and they can understand each other, and they can pick signal from the receiver. If the entire signal is picked up, then the leakage is less. If leakage is less, then the charging efficiency is higher. Okay, then the charging efficiency is higher. Yeah, so we try to maximize that. And resonance, basically, if you guys know about resonant converters, then resonant converters we know offers you soft switching, and soft switching basically is basically reducing the switching losses. Then right, yeah. So this is a universal topology. So what do you want to say for this universal topology? It has 8 things to do, or it has everything to do. Okay, a single circuitry. So if somebody asks you that, okay, I mean, is this topology yours? Of course it is mine. I will say yes, yes for forever. Okay, yeah, this is completely mine, yes for forever. Okay, so you understand this. You use grid, it will say okay. You use DC solar, it will say okay. It will, if you use another vehicle to vehicle charging in winter, it will say okay. Okay, if you are charging when parked stationary, it will say yes. When you are basically charging on the go while driving, it will say yes. Okay, when your battery is high voltage, it will say yes, diode rectification. When your battery is low voltage, it will say yes for synchronous rectification. Okay, so yes for forever, actually. Anywhere, everywhere, just yes. Okay, yeah, that's why I love this basically. Okay, now I will show you these operations one by one. Okay, in the first case, so this guy Sumantu, I mean in IIT Kanpur, right? So initially we use as a diode rectifier. We are not turning the switch on and off. Okay, if it is a high voltage battery actually, or if it is a grid to vehicle operation, again we are not doing it. Okay, now you can see this operation. So don't get carried away that these are basically waveform in the transmitter and receiver. Okay, which is here. So here is AC because this DC is converted to AC, high frequency AC. Then high frequency AC is again converted to DC. So here is DC, here is DC, but here is AC, high frequency AC and high frequency AC. Through resonance, because of resonance, you can get basically sinusoidal structure. But you can see the output is basically DC. Okay, yeah. This is the current and this is the voltage, because voltage is DC and it is boosted. So output voltage is basically DC boosted, but AC positive and negative bipolar. Okay, but current is sinusoidal. Okay, yeah. Now short switching, you can see the current is going down to 0. Oh, sorry, voltage is going down to 0, then current is start increasing. So you can see 0 voltage switching. So because of resonance, we are getting 0 voltage switching also. Okay, yeah. So that is the reason I was saying that we try to implement every merit. Okay, we try to implement every merit so that nobody can forget it. I mean, okay, loved by all basically. Okay, now this was transient converter, sorry, the transient response. So you can see that low current and then say high current. Okay, yeah. Okay, now, so this is for wireless charging that I'm showing you. Okay, now why synchronous rectification is required? Okay, so synchronous rectification, first of all, you need a MOSFET rather than the diode, so that current flows from the channel rather than the diode. So why it is so? Just understand some examples. Okay, so generally, if output voltage is 48 volt, then the switch you require, basically this bidirectional switch, sorry, this MOSFET is 100 volt. 100 volt MOSFET basically have approximately resistance of 3 milliohm. Okay, and if you are using diode, then diode, you can understand that diode will have a 4-volt voltage drop of 1.5 volt. Okay, now suppose if you are using, suppose 1 kilowatt. Okay, 1 kilowatt. So what is the current at the output for 1 kilowatt? Let us see, approximately 20 ampere. So that 20 into 48 is 960, 20. So suppose, since you are having, basically you are turning these switches on one time and this switch on another time. So basically at a time, basically 20 ampere flowing through this pair and 20 ampere flowing through this pair. Okay, so 20, 0, 20, 0. So basically average approximately for one time for one switch is 10. So if you see the losses, then losses is 10 square multiplied by 0 0.3, sorry, 0.003 3 milliohm. Also, let us understand 10 milliohm even. No issue, I mean. Okay. Or say 0.005 instead of 3. Multiply by 4, because there are four diodes, four devices. So it becomes 5 milliohm multiplied by 4, 20 milliohm multiplied by 2. So which is approximately 2 watt. Sorry, 0.2 watt, right? 5 into 4, 20 milliohm. Yeah, 0.2 watt. Or say if it is resistance is further high, you can still say 1 watt, 5 times more. Okay, so let us see. Okay, now if it is 1.5 watt of loss, power voltage drop, current is 10 ampere and multiply by 4 diodes. So what is the loss in the diode bridge? Basically, you can clearly see it is approximately 60 watt. So if you use a diode rectification, then the power loss is 60 watt. And if you use a MOSFET based synchronous rectification, the power loss is not even 1 watt. Or you can assume 1 watt or 2 watt or 5 watt even. 5 watt, I'm telling you, very high. That is the reason that when you have a low voltage battery charging less than 100 volt, and if you can use MOSFET for that, there is a drastic change in efficiency. Okay, because of this reason. Okay, yeah. So since as I was using this bidirectional technology, so I can implement synchronous rectification also and can improve the efficiency. Okay, another thing is that, okay, in addition to synchronous rectification, I can control them, their modulation. So by controlling this switch on and off, I can control basically their charging current. When it is a wireless charging, I mean the vehicle is driving on the highway, and the right side of the highway, the rightmost lane, basically having the coil on the ground. Okay, and then suddenly you pass through that and suddenly your vehicle gets power current. If it is diode only, then you have no control. And if the current is very high, more than the rating, then the diode will be damaged. Okay, and will affect the battery health and lifetime. But here, through the switch, you can control the charging current, keeping charging current within the limit of the battery specifications as well as within the rating of the devices, so that the operation is safer rather than you need to go for maintenance. Okay. So earlier I showed you a DC to DC part earlier. Now you can see AC to DC operation. Okay. So in this paper you can follow that. Okay. Since this is AC to DC, so we need to do active current wave shaping, because we did not do DCM. We use CCM. In DCM, no need of active current wave shaping. So you can see this is the grid current and grid voltage in unity power factor mode. You can see the envelope, high frequency envelope. Okay. The DC voltage and DC current. Okay. And this is the tank current, tank voltage, sorry. Okay. Yeah. So this is transmitter voltage, transmitter current. Okay. Receiver voltage and receiver current. Okay. And tested at 1.2 kilowatt. Soft switching. is still obtained. Okay, here you can see both actually, somehow a turn on also, a turn off also. Okay, yeah. Now transient results, you can see that for grid, somehow I think the student had some issues in wireless, so we did not increase the current change. We did not do drastic change actually, probably only 20% variation. But of course, I mean, sorry, 30% variation, 100 to 70 or 70 to 100. I hope you guys can do more than that. Yeah, but anyway, concept is verified. Now, the future, like today we don't have time, but the lecture I give nowadays is another is on connected vehicle. Right now the future was electrification. After a couple of decades, the future will be electronification. More electronics, more sensors, more data, telematics, wireless communications, sensors, networks, okay, and data analytics and decisions, so that you can avoid accidents, you can maintain road safety, you can do basically pedestrian safety, you can do proper GPS or route planning. Okay, you get all the info about road congestion, traffic congestion, red light, green light, or the behavior of other drivers, or people protesting in some area which is not for you to go, but choose another path. Okay, so this is electronification, where basically vehicle will be talking to the infrastructure, vehicle will be talking to another vehicles, vehicle will be talking to the pedestrian through the smartwatch. Okay, and then the driver will drive safely, reduce traffic congestion, and higher fuel efficiency or higher charge efficiency. Okay, yeah, so I think what is the time? So yeah, we have still 15 minutes for question answers. So that is all for today. That there is a possible to develop a flexible charging with roaming solution using a single circuit technology that I just showed you. It can be done through a boost converter. It can be done through buck boost converter also. Okay, and it offers you roaming solution that you can connect to vehicle, you can connect to solar, you can connect to DC charging infrastructure, you can connect to AC charging infrastructure. It can be done through plug-in as well as it can be done through wireless charging system. Okay, yeah, so that is all, and we'll be happy to answer any queries now. Yeah, any questions, we'll be happy to answer.
Good evening, sir.
Yes,
Sir, while doing that wireless power transfer, what is the efficiency you are achieving, sir?
say again.
What is the efficiency you are achieving while doing this wireless power transfer?
Yeah, in our laboratory it was 91%.
What is the distance between the coils you have set, sir? The distance between the coils, the transmitter and receiver coils.
Yeah, the distance was 25 centimeter.
Okay.
25 centimeter.
Okay, sir.
Any further queries?
Sir, good evening, sir. Sir, I have a question. Actually, we are doing simulation level. What is the power rating we have to develop the hardware prototype, sir, if we want to have a good publication?
For what application? I mean, it depends upon for what application?
No, EV charging. If we want to develop a wireless power transfer, what is the prototype power level we have to select, sir?
Yeah, I mean, at least 1 kilowatt.
Okay.
At least, yeah. Less than that will be difficult because low power wireless is not preferred first of all, right? Low power just do plug-in, yeah. So majority of the wireless power transfers are basically, at least 7 kilowatt or more. So we demonstrate at least 1 kilowatt for better. To better convince the reviewers actually.
Okay, sir. Sir, I have another question. Where can we get the coils and all, the core and
No,
this?
That we design in our laboratory.
No, the coil, the ferrite core and everything. Where can we get it? Do you have it?
That you can get from either DG key or Mouser.
Okay.
Or you can directly purchase from Coilcraft and ferrite TDK ferrites also.
Okay. Any ready-made, if we provide a structure, if they are providing anything, okay, if I'm designing a circular coil, okay, the specific diameter, everything we will give anywhere they are providing the readily available coils.
There are some basically. There are some. I think Coilcraft send some.
Okay. Sir. Thank you, sir.
Coilcraft can give you that, yeah.
Okay. How can we approach them, sir? Directly we can call through website, sir? Or?
Yeah, just email actually. They have a form. If you open Coilcraft website, they have a form, and then in the form you can mention your requirement, and they can send you many times. You can ask for some samples also. They are ready to give some samples as well.
Okay. Yes, thank you.
So I hope you like this. Basically, that one technology can do many things, not just a DC to DC, AC to DC all the time. I cannot hear you, Madhu madam. Cannot hear you.
Yes, so the beautiful thing was that the same topology, this DC boost converter, buck boost, that can be used for the transfer from AC to DC and DC to DC. So that is the good thing in the circuit.
Yeah.
Okay, now we can end the session. So thank you, Professor Rathore, for your insightful lecture on vehicle to vehicle, vehicle to solar, and vehicle to grid technology, along with the wireless charging circuit topology. So we have get a very good idea. You have shown the hardware work, and even the MTech students, she has done a very good job, and her waveforms were very clear and very nice work she has done. So it is a very good inspiration for the PhD scholar, and I think the faculties as well. So is paper is available?
Yeah, they are available online in IEEE. Yeah.
Okay, sir. So if anyone want to do the work, they can refer the paper. Okay. Thank you so much.
Thank you very much. Yeah. Thanks for this opportunity again.
Yeah.
Okay, I will exit now. Huh?
Okay, sir.
Yeah. Thank you, everyone. And if any queries, just feel free to email. Huh?